Hello, and welcome to the latest iBwave webinar. Today's topic is algorithms behind the heat maps, how prediction methods impact prediction accuracy. I will just take a few moments to introduce our presenter today. Our presenter, in case you don't know him, is Vladan Jevremovic. He is our research director here at iBwave. Vladan has over 20 years of professional experience in the wireless industry. And at iBwave, he is in charge of RF propagation and optimization algorithms applied in building RF design and planning tools. Vladan also develops technical courses offered through iBwave certification program. He holds a PhD from the University of Colorado. He routinely contributes to research through white papers and case studies, and we're very happy to share that just recently, a whole chapter of in-building case studies was contributed by Vladan in a new book on indoor wireless communications. It's available through Amazon if you want to check that out. Also, if you're headed out to WLPC in Lisbon, Portugal, or CWNP in Orlando, USA, Vladan will be speaking there on the dates stated on the slide. And just a few housekeeping items before we get started. You will receive a video recording of the webinar by email within the next few days, so keep an eye out for that. And also, if you want to ask any questions, please use the questions box in GoToWebinar, and we will try to answer as many questions as we can towards the end of the session. Okay, just a few things in case you don't know who we are. iBwave is the worldwide standard for in-building network design and documentation. We are a global company trusted by over 900 customers worldwide. We offer a full solution enabling all phases of deployment lifecycle for your wireless projects, regardless of technology, and we're continuously innovating to improve our product suites. Now I will hand it over to Vladan to get us started.
Thank you, Imna. Hello, everybody. Good afternoon from those that are in North America. My name is Vladan Jevremovic, and I will be talking about the algorithms behind heat maps, specifically about algorithms that exist in our products, iBwave Wi-Fi, iBwave Enterprise. There are three different algorithms that you can choose from in our solution. The first one is, and we will talk about that first, about COST 231, wireless PathLoss Exponent, and ray tracing. And then we will talk about accuracy of those three in case study section, where we will see what is going on in office space, hockey arena, and shopping mall. Then we'll make a conclusion as to what would be the most appropriate scenario to utilize each of those three propagation algorithms. And then I will treat you to a demo that will show you how to model inclined surfaces in our tool. Why is it important? And we will also talk about calibration. I will show you how to do calibration of propagation algorithms in our tool. So let's get started. First, we talk about those three indoor propagation algorithms that you can utilize in our tool. The first one is COST 231, and this is a very well-known algorithm that takes into account only direct path. This model has a few different terms that you see in the equation. The first one is the path loss at a distance of 1 meter. The second one is free space path loss, that is a function of a distance. And then what we have is penetration loss. The very last term is penetration loss due to signal penetrating walls. So we have the penetration loss of each wall type and the number of wall types that are in the path between transmit and receive. And this busy looking third term, this is really a penetration loss in between floors. So the beauty of this algorithm is that it can be used in Excel. When you do that, you would be estimating the number of the walls between transmit and receive, and also estimating the type of the walls between transmit and receive. So if you are doing the estimate, that is not very accurate, but it is very inexpensive way to do it because everybody has Excel spreadsheet. However, this particular algorithm works best with access to CAD floor plan and material penetration loss database. So what are the pros and cons of cost 231? The pros, as I mentioned, is fast calculation. Even if it is not in Excel, even if it is in a computer using CAD file, it still is going to be very fast because you only have a direct path between transmit and receive. This is a good signal accuracy prediction when used with CAD files. Excel files, I would just not recommend that. It is just too many assumptions. The cons is there is only direct path accounted for. There is no reflected or diffracted paths. And because of that, as in particular because there are no diffracted paths, the heat map would show unnatural looking shadows, especially away from the antenna. The more the complex the venue, the less accurate the prediction. So we will see that later on. But this is how it looks like. You see this is an office space. What you see here is a break room in the top corner, and then there are individual offices around, and in the middle is cubicle area. So antenna is pretty much in the middle. And then what you are seeing is shadows that don't look very natural. Okay, you have a very sharp drop when you move just a little bit. And this is not really what you should expect in real life when you go out and observe how the signal changes when you are not in line of sight. The signal should not drop all of a sudden 10 dB and stay there. Then there is the second algorithm that actually we developed. It's a variable PathLoss equation, and this is also a direct path model that takes into account three terms. The first one is that same unity distance, unity path loss at 1 meter. The second one is a function of a distance, but instead of 20, it has 10 times n as a term. This n is a path loss slope for a given RF propagation environment. Okay, so what exactly does that mean? It means that we recognize that different venues will have different RF propagation environment. Some would be fairly open, like warehouses. They really do not have all that many obstacles, or let's say airport terminal. There are some, but not that many. Then there's going to be the ones that are very dense in RF term, but it means, for example, if you are in a hospital, you will encounter many rooms with heavy walls. When I say heavy walls, that would be concrete walls or brick walls or something of that nature. So recognizing that there are different RF propagation environments, we have identified 5 that we actually can choose from in our tool. So what does that really mean? It means that when you have a layout in front of you, you basically have to make a decision what that particular layout looks like. Does it look like a cubicle office? Does it look like a shopping center? Does it look like a hotel? And once you do, you basically have to assign that layout to that specific RF propagation environment. And that is how this formula is calculated. Once you do that, once you identify that, we actually will give you from our table n, which is PathLoss slope And then we will also give you the free coefficient, which is A, and then this path loss can be calculated. So what are the pros and the cons? The pros is this is a direct path model, so that means fast calculation. And this can be used directly on images. You really do not have to draw walls around or anything of that kind, because you are assigning RF propagation environment. And while you can assign a single RF propagation environment on any image, you can also assign multiple ones. It will just take you more time. And that is also a con, because user needs to define one or more RF propagation environments, and defining more will increase the accuracy. Speaking of accuracy, this tool has limited accuracy because you don't have walls, there is no penetration loss. You only have RF propagation environment, which its own associated path loss slope and free coefficient. So that means the more complex the venue, the less accurate this prediction is. And you will see how this works in more complex RF environments later on. And this is how it looks on the same example as you have seen before. This signal drops at a steady pace away from the antenna. There is nothing exciting going on here, and it is like as if those walls don't exist, and that's because this formula does not take wall penetration into loss. But it does take into account that you are in an office environment, so the characteristics of the path loss slope and the free coefficient are such that it takes that into account. And then ray tracing. So what is ray tracing? Well, this shows what it is not. It is not a guy named Ray and you're tracing around him. It is about electromagnetic rays. Electromagnetic rays that exist between transmit and receive, and you have to figure out where they are, and you have to figure out to be able to describe them properly in order to account for them properly, so that you can calculate your signal distribution in a venue. So ray tracing is a method. This is how it looks like. You have a direct path that is shown in red. Then there are many reflected paths that bounce off the walls multiple times when they leave transmitter before they get to receiver. And then there are diffracted paths. Those are the ones that hit the edge of an obstacle and then curve around it and then come into the receiver. So this is a fairly well-known technique, has been known for quite some time, and we actually have deployed a variant of it in our tool. It works only with floor plan CAD and material penetration loss database. You cannot get away with doing this on Excel spreadsheet. So there are many pros as to why would you want to use ray tracing. There are more propagation paths between transmit and receiver, and it gives you a better accuracy. You can accurately predict signal in complex three-dimensional venues, such as stadiums, arenas, multi-level subway stations, and high-rise towers. You can model inclined surfaces as well. Cons, well, ray tracing is very computing intensive. So much so that while this has been known for many years in academia, they would use this and they would then have a fairly simple venue analyzed with full ray tracing for several days. So that is really not something that we can afford. We have a commercial software, so while our customer may be okay with having the propagation analysis for a couple of hours, maybe several hours, they would not be okay for, let's say, analyzing a stadium for several days. So we came up with some limitations. We limited the number of diffracted and reflected rays ways to speed up computing, and we named this method fast ray tracing because it really is not a full ray tracing. So how the fast ray tracing look like? Well, you see, it looks at first a bit like cost 231 because we still have some shadowing here in the back. But in the next case study examples, you will see that there is quite a bit of difference once you get further down from the antenna. And I will explain why that is, why would that be important. So, again, we will go into examples next. This is just a comparison as to how this looks like in a familiar environment, which is an office environment. So now onward to case studies. The first one is office space. And this, we took measurements at 2.1 gigahertz with a continuous wave equipment. And there were 3 antenna locations. One was outside of the office, the one was in the break room, and then there was one in the middle. And you see the areas that we traversed that are marked as survey trays. I'm going to pause here for a second just to explain to the Wi-Fi guys on the call why would that be relevant to what they are doing. 2.1 gigahertz is very close to 2.4. So the result that you see here is, something that would be easily translated to 2.4 gigahertz. And we did those measurements a while ago, and we basically decided to use that as an example even when we talk to a Wi-Fi audience. So when I later on go about doing the calibration, it will be with a 2.1 gigahertz data as well, even though you can do calibration at iBwave PC Wi-Fi with no problem. So having said that, what we are going to do is do signal prediction maps for those 3 antenna locations and compare with CW measurements for all the 3 propagation algorithms at those 3 locations and see what the accuracy is. So before I start diving into key performance indicators, I just want to invite you to stop and look how those 3 look like. For VPLE, we have a steady drop in a signal, which is what we expected. But look at the difference between FRT and cost 231. There is a lot of shadows in this area, very unnatural looking. And you don't have that much in here. So how does that translate to accuracy? Well, look what we have here. I have 3 KPIs. I have mean error, absolute mean error, and standard deviation. Mean error, it's nice to have. It is not all that useful because you can have an equal number of positive and negative values with the same distribution, and you will have mean error of 0. But at the same time, your absolute mean error could be 10 dB. How is it possible? You have plus 10 in large measurement, minus 10 in large measurement. So while it will cancel out for mean, with the absolute error, it will still be 10. So, okay, so absolute mean error is of 6.7, but interestingly enough, standard deviation is not all that high. On the other hand, cost 31 is really bad. The absolute mean error is, what, 11.4? And standard deviation is 7. High standard deviation, high absolute mean error. And that is because of this area right here. So you can then point out and say, well, why does it matter? This area has a poor signal anyway. Well, if you look into what is going on, here is that you will see that that area is actually should have been fairly high in a signal. If you see from the legend, right? It is very low with cost 31, but should be higher. And so really what you will have is interference signal coming from this antenna, assuming there would be another one right here that is fairly high. and that would affect your signal to interference and noise ratio or co-channel interference if you are a Wi-Fi guy. Whereas here, you would just say, oh, that signal is just way too low. It will not affect my co-channel interference or SANR. Now moving on to location number 2, which is in the break room. There, I still see a bit of a shadowing phenomenon here, but not as much. So what that translates to is that I have comparable values for absolute mean error for COST 231 and FRT, but standard deviation still is a bit better for FRT than for COST 231, which basically is meaning, well, yeah, this area may not be, big enough to affect my absolute mean error to shoot it up, but it affected my standard deviation. VPLE is, interestingly enough, in those two cases, not doing all that bad, and it is only about a dB off of FRT in this example. In the previous example, it was a little bit better than FRT by a dB. So VPLE is doing well. So this may be a good choice for using the VPLE. We will get to that a little bit later. Now, the next one is antenna location number 3 when you are in the middle of the office. And there you see that the shadowing, the shadow effect is about equal, a little bit better than FRT. The accuracy is comparable with absolute mean error and standard deviation between these two. This VPLE is a bit off. So what I can conclude from Office Space is that both COST 231 and VPLE have their moments. They do have a bit of accuracy in 2 out of 3 cases, but FRT is very consistent. It will give you between 4 and 5 dB accuracy, with no problem. Now there is a bit of a more complex venue, which is a hockey arena, and we took measurements at 2.1 as well. They're taken at 3 levels with 2 antennas. So this is antenna number 1, and here is antenna number 2. And these measurements were taken below antenna number 2. So we will do prediction of signal heat maps compared with CW measurements for the 3 algorithms at 3 different levels. So this is antenna location number 1, and I will just focus on absolute mean error and standard deviation. FRT is very accurate. I mean, very accurate, accurate as we would expect, between 4 and 5 dB for absolute mean error in both interior ball, which is right around this edge, and in a corridor, which is around here. VPLE is not doing that well in a corridor, which is here, and decent accuracy on the interior, considering how simple this is. Now, COST 231 is, I would say, about 4 dB worse than FRT in absolute mean error, and standard deviation is about 5 dB worse, maybe even 6. So you see how it natural looks like. It really shines through, how you have a steep drop from yellow, to immediately, to dark, to light blue, or even, dark blue. Very unnatural looking and not very accurate. The next one is, again, very consistent default prediction. By the way, all those predictions are default predictions for FRT and all others, between 4 and 5. This one is not doing that well. It's 4 to 5 dB off, except for interior ball. And this VPLE is now breaking down completely, as you see Interior ball, it's 22 dB off. Backstage, 18 dB. Backstage return, 14 dB. It just does not have any use. It's only in visitors' locker room. It is a bit better, and the reason for that is that visitor locker room is not a very big space. It does not really have all that many obstacles in between. And then this is not really antenna location number 3, but level number 3 coming from antenna number 2. There you see that you have a comparable performance between FRT and cost 231. Even their standard deviation are not all that different in, between them. VPLE, on the other hand, is still performing poorly. So, to conclude, in NHL Arena, FRT has been very consistent. Cost 31 had maybe a couple of times that a couple of runs where it had not as bad accuracy. For example, here we have those two were okay, and there was one on the previous slide, but past that, majority of them were vastly more inaccurate than FRT. And that comes from the complexity of the venue. Now we go to a different venue, which is also a complex 3D structure, which is a shopping mall. And there we took 4 antenna locations as measurements. So this is one is corner. This one is, which is the entrance to the mall. This one is the entrance to the Sears or Dillard's or whatever. And then another entrance to the mall and another entrance to the mall. So let's see what's going on. What you see here is what is happening when you start measurements from this point and then you go all the way over here. So what's going to happen is that you will see now clearly that FRT has its own issues with shadowing, but those issues are on the very far end of what we call acceptable distance. Remember, this is a shopping mall. So the distance between the entrance and the exit is, I would say, about 150 meters, probably. And you would not expect this antenna to have a signal anywhere further than this. But even for interference, I would say somewhere around here, the influence would stop. Things are worse at cost 31 because that shadows start, much sooner for them than for FRT. And so the accuracy is a bit better. It is about 4.8 here and 8.1 over here. So it's a little bit over 3 dB better for FRT than cost 231. And the difference in standard deviation is also about 3.5 dB. VPLE, not very good at all. And this is going to be the theme for the rest of those antenna locations. VPLE is breaking apart completely. It just does not have any accuracy. And you see what's happening here? Very interesting is because you have almost equal amount of points that are positive and negative with the opposite sides, because your mean error is 0.4. So your absolute mean error is high, so you would expect the standard deviation to be very high, which it is, which is close to absolute mean error, because you're essentially canceling out your measurements on the opposite side of the positive and negative sign value, which is not the case with the other two, but still FRT is better than a cost 31. Then we go to another antenna location. Again, VPLE is falling apart. Again, FRT is better than cost 31 by a bunch of dBs, and this is going to continue with antenna number 4. Even though I have to say that here for the first time we see the FRT having a fairly large absolute mean error, almost 8 dB, and standard deviation is still okay, but what it means is that mean error and absolute mean error are in the sync, which means that you have I'm consistently having the error on one side of the equation. So if it is prediction minus measurement, then my prediction would be consistently higher than the measurement, or the other way around. And similar thing is going on with the cost 231 as well, only they have a worse accuracy. So what does this all mean? It means that we would recommend FRT for complex 3D venues like stadiums, arenas, high-rise towers, shopping malls. However, cost 231 can be used for less complex venues. What would be those? Well, office space. You'll see that it had good accuracy there. But what about VPLE? We have dutifully included them in all the analysis, and we see it's not very good, except that, you know, it was in office space. It was kind of okay. Well, what we actually had in mind when we developed this was field technicians that go on site surveys. So let's say that you are a field technician, you're going on a site survey, you have a tablet, and you would want to, you know, get the floor plan and import that floor plan into your tablet, and you would want to walk around, identify locations on that floor plan, and take a picture, and then take a note about, you know, what you've seen there. And perhaps even you would want to drag and drop AP from the database onto the floor plan and do a quick analysis of the propagation from the point that you have identified. Well, this is the tool for that. This is the tool for site survey, for field technicians that go out with tablets that don't have much computing power, but they would want to give you a preliminary bill of materials and notes from the site survey. So this is for them. And we have a product for them called iBwave Wi-Fi Mobile, and iBwave Wi-Fi Mobile does have VPLE. So when the technician is done with the site survey, he would upload this to a cloud, and we have a product called iBwave Unity, which is our cloud and much more. Then engineering team can download that and take a look at the notes and pictures and preliminary design, and then, you know, get the venue in a CAD format, and then, you know, import the CAD format and do the real design based on what the technician has given them. So this is how we envision all this. iBwave Wi-Fi will have all three algorithms. iBwave Wi-Fi Mobile would only have one, and so that's how we found a place for VPLE, and that's why we have developed VPLE for field technicians. And now, demo, we will talk about inclined surfaces and calibration. So I will go get out of the presentation mode, and I will then go into a arena, which I will give you a 3D view of. And then I will just first remove those prediction images so you can better see how it looks like. So, okay, so basically this is your basketball arena. And the inclined surface that you see here is an inclined surface, a seating area. And all those little dots are basically access points that you can locate. And you see even the basketball, you know, time left in the game is, you know, shown here, which is kind of really cute. So what you should expect when you have this level of detail to model is probably to spend about a week doing the modeling of inclined surfaces, seating areas, and all those private boxes, and even those, you know, handrails for the area when you step down toward the seating area. But what you would get in return is very good accuracy of the modeling. So yes, you may spend a week doing this, but in the end, the payout is going to be something, a design that you can be confident in. And I would like to show you what I mean by that in the next example. My next example is going to be the metro station, and here is a metro station that has escalators. So this one is an escalator, and I'm going to show you that in a 3D plan. So as you see here, it is horizontal. Okay, that yellow area right here, we model this as horizontal. Just to get your bearings, this is where the access point was on the previous two-dimensional screenshot. And I'm going to remove the prediction image, so you can see that this really is very flat, very horizontal. And this prediction image is telling me that I'm doing okay there. It's telling me that I have a signal between neg 75 and neg 65. All right, so that's when I do the things incorrectly. What happens if I do things correctly, if I model this as a inclined surface? Well, the signal is much less. It's between 95 and neg 85. That's a 20 dB difference. That's a lot. And just to prove a point that this is really an inclined surface, I'm going to show you how it looks like in 3D. So again, this is AP, and this is the inclined surface, the escalators. And when you go in and remove the layers, prediction images, you will see that this is indeed the inclined surface. So escalator goes up and then flat, up and flat, up and flat. So you see that there is a 20 dB difference that you make if you take the lazy approach. Even this is a metro station, so you think the escalators are not all that important. Yes, they are, and you will have a poor coverage if you do not remember to model them as inclined surface. Well, having said that, this is iBwave Wi-Fi PC, as you can see. And now I'm going to switch to our different product, iBwave Design Enterprise, to show you how to do calibration in our tool. And what would you expect from that? First things first, I have to tell you that when doing calibration, you have to have two sets of data. There's a reason why you need to do that. It is because if you cannot use a single set of data for calibration and for validation. It has to be different. They have to be different. There are two ways to do that. The first one is to have one data collection run and then take every other data point. So that way you end up with two sets. Okay, basically you split your original data into two. The second one is to take two runs. One is going to be collecting data for validation and one for calibration. But regardless how do you do that, what you need to do first is, and I'm here showing you both. One is called valid, one is called calib, because one is for calibration, one is for validation. So this is both of them. So now what I'm going to do is I'm going to only show one of them. And then I'm now going to do a very important thing, which is a first step, and that is to remove fast fading. So why am I doing this? It's fast fading is multipath, and I don't want multipath. I want to remove the multipath from calibration, and the only thing that's going to stay in there is slow fading and a median path loss. Okay, so there for what I'm going to do is I'm going to say the wireless services are going to be the one at 2100 megahertz, and I click on fast fading averaging removal and selecting that, and I'm going to do a run, and I say okay. So you see now I have fewer points than before. The density of the points is not the same. So now I'm going to basically say I don't want this. I want this guy. and do the same thing for that as well. Both times select plotted data as raw data and fast food average, fast fading average, not fast food. Fast fading averaging is, yeah, so now how many wavelengths? Between 5 and 20. What is my recommendation? Well, if you are doing at 700 megahertz, choose 5. If you are using at 850, choose 5. If you are using higher frequencies, you know, from 1900 and up, you can choose either 10 or 20. I'm choosing 10 right now. So this is done now. So I have removed fast fading for both of them. Then what I need to do next, I am going to run a prediction using default or uncalibrated values. And then I'm going to go to reports and say prediction versus measured data. So I'm going to choose validation data. And okay, so I have a fairly high absolute mean error of about 8 dB and fairly high standard deviation of 9.5. So let's remember those two numbers, 8 and 9.5. Those are the mean error, absolute mean error, and standard deviation for default prediction. So now let's do calibration. I'm going to go to prediction and say calibrate and select this antenna. Select all and then use calibration data to do calibration and call this calibrated and then make a run. And then assign that model to that antenna. Once I do that, I'm going to run this again because I now am running this with a calibrated model. And then in reports, I'm going to say, okay, let's compare those now. Remember, we had 8 and 9.5 as values. So now, instead of 8, I have 6 as a mean error. Instead of 9.5, I have 7.7. I have improved about 2 dB for absolute mean error and standard deviation. And this is standard. This is what you would expect, between 1 and 3 dB improvement once you do calibration. So the value of calibration is basically you get more accurate prediction, which is what you would expect. But now I have shown you what steps need to be taken. You basically need to have 2 sets of data, one for calibration, one for validation. You need to remove fast fading. And once you do that, you are ready to do your calibration. One other thing that I wanted to point out is you see that mean error of that is close to 0. This is how it should be. It should be close to 0, but it should not be 0. If you see this error to be 0, it means that you have used the same data for calibration and validation, which is not something that you should be doing. And once you do that, don't be very proud of yourself either, because it is the wrong way to do things. Having said that, I'm going to turn back to the microphone to Amna, and we are going to start with the Q&A session.
Okay, thank you, Vladan. So let's get to some of the questions. The first question is, what are the effects of cell loading percentage on prediction?
All right, so cell loading. I'm assuming that this is a question that comes from cellular world, from LTE in specific. And so For those that are with Wi-Fi, cell loading is very similar to airtime utilization. Basically shows how many resources, how many resource blocks are busy in a frame, in an LTE frame, and then so the more populated LTE frame, the more busy those resource blocks are, the higher the cell load, and the lower the SANR. If the SANR is lower, then maximum achievable data rate drops as well. So if you have a busy base station, your cell load is going to be high, but your SNR is not going to be doing all that great, and your data rate will suffer. Your maximum achievable data rate will suffer.
Okay, so the next question is, how do you predict SINR?
Okay, well, first of all, you have to take into account that you have two different types of SANRs. This is SANR a reference to PDSCH. Again, this is a question that comes from LTE world. SANR reference to PDSCH, which is a resource element that is used to carry data in LTE, and SANR reference to reference signal, or RS, which is basically something that is close to, let's say, a pilot signal in WCDMA. So having said that, it is always your serving signal, be that a reference signal or PDSCH resource element, divided by some kind of interference, right? And that interference can come from the external sources, which would be let's say, neighboring eNodeBs, or internal sources, which is basically the resource elements that exist in the same OFDM symbol, but are not of the same type as the one that we are calculating SANR of. For example, what you would do with a SANR for a reference signal is you have OFDM symbol that has RS in it, but has others, right? So those ORF symbols that are others may basically be considered as interference. Similar thing for PDSCH. So that's in a nutshell how you calculate SANR.
Thank you, Vladan. So another question is, how do you predict MIMO? Do you show multiple paths or just use an offset for the MIMO gain?
Right. So I'm going to show how we do that in our tool now. So going back here. So in properties, we have this item called MIMO. And there, let's say you can use 3x3 MIMO, or let's say 4x4 MIMO, right? So the way we do it is we do not calculate antenna 1, and then antenna 2, antenna 3, antenna 4, which basically that would quadruple our computing time. Instead, what we do is we calculate SISO, maximum achievable data rate. How we do that? Well, if you have, let's say, SANR of 20, you may calculate that your maximum achievable data rate, let's say maybe 50 megabits per second. I'm just giving you an example. I don't know what it is. And then so you do that. Your maximum achievable data rate for SISO is 50 megabits per second. But then you look into this table and you say it at 20, SNR of 20, I have throughput gain of 3.6. So I would multiply 50 with 3.6 to get 180 megabits per second. So that's what I would expect with 4x4 MIMO. That's how we do it in our tool.
Thank you. Another question is, how are algorithms affecting arena predictions when there is a rooftop?
Okay, so there would be arena with the rooftop, and there would be without the rooftop, and then there would be with the sliding rooftop. So I'm going to tell you what would happen with the sliding rooftop. Let's say that the weather is nice and you have an open arena and that you are a cellular engineer. Okay, so in that case, you have a signal coming from the neighboring macro stations coming into your arena through the open roof. That is interfering signal. So you're not happy about that, but what you do is you are going to design your system with the worst case scenario in mind. So you let that signal come in and treat it as interference. And then you figure out what your SNR would be and figure out the maximum achievable data rate, and that's your design. What happens if it rains outside, the roof is closed, and that blocks that signal? Not all of it, but it blocks it a bit. Okay, so now your signal coming in that is interfering signal is reduced, so your SNR is better. And then you also, what you have is the signal bouncing off of the roof from all the sources from the inside. Okay, so those sources from the inside, you know, would be some good, some bad. So that may argue this cancels out, but because you have less interfering signal from the outside, your SNR is better and your MADR, maximum achievable data rate, is better. Now for the Wi-Fi, there what you would not have on the much of a macro signal, so opening or closing the roof would not really make that much of a difference. For for what's going on inside, it basically would affect both call channel signal and you know, the signal that you like, your serving signal. So at the end of the day, you may have your SNR a little bit better, but your call channel may get worse. So that's how would that affect Wi-Fi.
Thank you. Another question is, are these prediction models the same for desktop and mobile?
No, iBwave mobile only has VPLE, and desktop has all three, FRT, VPLE, and cost 231.
Thank you. So another question is, are manufacturers' radios already added to the AP models with their specific outputs for the wireless?
Yes, APs are basically modeled by manufacturers, and they exist in our database. So when you access an AP, that has been put in there by manufacturers, modeled by Cisco, Aerohive, etc., etc.
Thank you. Let's see another question. What is the best model to use for a venue with a lot of reflections due to metal surfaces?
Well, first of all, if you have a lot of reflections, a lot of multipath, okay, in a venue, well, first of all, I don't know if this is coming from you know, Wi-Fi world or LT world, but the reflections and the multipath, it used to be a big problem before MIMO came in. MIMO really thrives in this environment if you have lots of reflections. So I would definitely use a MIMO system. I would not use a SISO system for a venue like that. And then, you know, because when we talk reflections, then cost 231 would not be in play, because cost 231 cannot model that. VPLE cannot model that, so you have to use FRT.
Thank you. Let's do one more question. Can FRT take MIMO streams into account for ray tracing?
That was kind of answered with my previous question. We really don't count separate MIMO streams. We calculate SISO and then apply MIMO gain to give you an estimate of maximum achievable data rate in N by N MIMO. We do have 2x2 MIMO, 3x3, and 4x4 as of right now, but we do not calculate separate streams for MIMO, only one.
Perfect. So those are all the questions we have time for today. And I would just like to remind everyone that we will be sharing a recording of the webinar with all of you shortly. And if you have any more questions, please feel free to reach out to us. You can also look at our past webinars on our website, iBwave.com. And once again, thank you everyone for attending, and thank you, Vladan, for this presentation. I will now end the webinar for everyone. Have a great day.